This is lecture 40 of the course on high performance computing. For the past few lectures, we have been looking at parallel programming. We had a brief look at characteristics of parallel machines. We understand that a parallel machine is a computer system in which there is more than one processor. This could range from something like a cluster of workstations, a cluster of PCs, in other words a network of computers, to a specially designed machine which has multiple processors sharing physical memory. We are in the process of trying to understand more about how to program a parallel machine, not using shared memory ideas which we saw during our discussion of concurrent programming, but rather the programming of parallel machines using the message passing idea, which we had mentioned earlier, but we are now looking at in more detail. Now, in order to program, to write parallel programs in which the individual processes communicate with each other through message passing, there must be support provided by the underlying operating system on which which runs on the individual processors of the parallel computer, and this must take the form of what I will call functions provided or supported by the operating system for the explicit sending of data from one process to another, such as in this notation which I am using here. This particular notation is not standard to any particular system, which is unfortunate in that it becomes necessary for the programmer to learn the specific details of sends and receives, as these functions are often called, on the different operating systems or systems on which the parallel programs are to run. Fortunately, we have message passing libraries which abstract that away, making it unnecessary for the programmer to learn about the individual systems, but rather just has to learn the library functions of that particular message passing library. And we are talking about MPI, message passing interface, which is currently a fairly popular library for the message passing programming of parallel computers. These are two good references to read regarding MPI. And as I mentioned, MPI is a application programmer interface for writing message passing parallel programs, which hides the hardware and software details of the underlying system, thereby making it possible to write portable programs, parallel programs which you could run on one machine and then without any change to the program run it on another parallel machine, as long as both the parallel machines support the message passing interface MPI. MPI is implemented as a library. So as far as you are concerned, you write your what I'll call MPI program. Make sure that you run it, that the system on which you are going to run it supports MPI, in other words that the MPI library is available, and subsequently, regardless of whether the system uses very standard hardware and software or custom designed hardware and software, your program will be able to run on the system, which is the portability advantage. I had briefly looked at some of the key functions in the previous lecture, key functions and constants of MPI. We noted that all the MPI functions and constants start with the prefix MPI underscore, making it quite easy to recognize them. An MPI program must be written to start by initializing itself as far as MPI is concerned using the MPI init function, and as you would possibly imagine, what this function may do is to set up the infrastructure. It's possible that it needs to set up some buffers or it needs to set up processes on the individual compute nodes in order to allow the message passing communication to happen. Subsequently, the programmer must know how to do sends and receives, and we must understand the details of the send and receive functions more carefully. And in these function calls, one may need to make use of certain predefined constants which are given. Rather than having to use the value of the constant 0, 1, 2 or 3, one could use a name for the constant which gives the program a better readability. So we do need to understand more about these functions. We will manage with approximately with an understanding of about 10 functions overall, which will be adequate to write most of the parallel programs that may be of interest to us. Now, one question which will arise before we move to the individual functions is how does one construct an MPI program? With the discussion that's going to follow in this lecture, we will know how to write an MPI program, but obviously that MPI program will subsequently have to be compiled or something of that kind before it can be executed on a parallel machine, and that is what I am referring to by the word making. How does one construct and write a parallel program and then cause it to be transformed into a version that can be executed on a parallel computer? Now, the thing which must be noted is that in compiling an MPI program, one must of course make sure that it is linked with the MPI library functions, because when you write an MPI program, it will be using the functions that we had seen on the previous slide, and they are not present in your program since you did not write them. and they are present in the library, which must therefore be incorporated into the executable version of your program by linking. And this is similar to the way that you had to link the math library if your program was using a math functions. So just like there's a math.h header file, there is an mpi.h header file in which the declarations and definitions are contained, and subsequently by the linking of the correct mpi.o file, the various functions would be incorporated for use by your program at runtime. Now, in the previous class I had talked about the different versions that a program may take depending on whether one is running the program on an MIMD parallel computer using Flynn's classification or on an SIMD parallel computer. And I had used the notation SPMD, standing for single program multiple data or for shared program multiple data, as a kind of a programming model which could be used to program, let's say, an SIMD computer. Now it turns out that in MPI people commonly use this SPMD mode. In other words, they write a single program which generates a single executable. This executable file, what I mean by an executable is an executable file like an a.out, and this executable file would then be run on each of the processors, each of the nodes of the parallel computer. So it's the same program that is running on each of the nodes. And we have seen an idea like this when we talked about concurrent programming. You'll recall that we talked about the possibility of writing a program which runs as 2 or 3 processes. So one would write a single C program, let us say, and one would compile it, and then one could run the program. In the context of concurrent programming, there was no question of running it on more than one processor, because we were talking about a situation where there was only one processor. But the program could run as multiple processes because we may have included the fork system call, which caused a new process to be created when the program was executed. So in that sense, what we were doing in that form of concurrent programming was to write a single program which would run as many processes. And the idea that we're talking about over here is similar. Rather than writing a separate program to run on each of the nodes of the parallel computer, we write a single program which contains information about what all the different processes which are cooperating towards the common objective are going to do, along the lines of what we did in the case of the concurrent program. You'll recall that in the case of the concurrent program, we looked at the return value from fork to determine whether the process which was executing at that point in time was the parent or the child process, and depending on the return value we would then move to a different part of the program to do what the child had to do or what the parent had to do. And something similar could be done for an MPI program, where depending on the identity of the process which is running the program, a different portion of the program could be executed, thereby allowing many different activities to be described. So this is one of the more popular modes of writing MPI programs. MPI programs could be written in different modes as well, where you have a different executable for each of the processes. The simplicity one gets from this is that there's a single executable file which would be run on each of the nodes. So multiple instances of it executed in parallel, one instance of it, of this executable, running on each of the processors of the parallel computer. Subsequently, there is the other issue which we had talked about last time. How does one actually cause, let's suppose I have a parallel computer with 1000 nodes, then I would have to cause this executable file to run on each of the 1000 nodes, which would take a long time for a human being to do. One would have to type a.out on the shell prompt of each of the 1000 processors constituting the parallel machine, which would take a long time. So fortunately, the implementations of MPI will typically provide you with a command, which is often called MPI run, through which you could cause the initiation of the 1000 processors to happen through the services of MPI run. So the single executable file, the single a.out would be taken as input by MPI run and run on all the 1000 processors. Now, depending on how many processors you want to use on the parallel computer, you could provide inputs to MPI run. So the options to MPI run would typically be the number of processes that you want the MPI program to run as, and if you have sufficient knowledge about the parallel computer, specifically which processors of the parallel computer you want the different processes to run on. As you can imagine, if to specify a processor of a parallel computer, one would have to have processor IDs of some kind, and therefore it's more often useful to try to think of the scenario if one was writing an MPI program to run on a network of computers, in which case each of the computers in the network would have its own network address or IP address, and one could possibly specify the individual processors in that form by the IP address of each of the processors in the parallel computer. But these are the two options which MPI run, a typical implementation of MPI run would take: the number of processes that you want the program to run as, and further possibly the specific processors where you want the processes to run. Now this is an interesting idea because it suggests that you could write an MPI program without taking into account the actual details of how many processes it is going to run as. So you could write an MPI program so that it runs as some n processes, and then you could actually run it as 16 processes one day or as 32 processes the next day without actually changing the program, but by just providing the correct information about the number of processes in the initiation of the execution of the program through MPI run. Okay, now one of the important concepts in MPI is what is known as the MPI communicator. And you'll recall that when we talked about send and receive, I pointed out that it's critical that the identity of the sender and the identity of the receiver must be known, because in doing the send, the program of the sender must mention the intended recipient. So there's this need to have the identities specified within the program, and therefore to distinguish between the different processes constituting the MPI program. And central to this is the notion of a communicator. Basically, a communicator is a mechanism to define a communication domain for a given communication operation. Essentially, the set of processes that are allowed to communicate among themselves. So an MPI program could be written to have many different sets of processes depending on what the communication requirements of the program are. Let me just give you a very simple example. Let's suppose that I'm writing a parallel program which has, let's say, which I know is going to run as 4 processes, but I know that in achieving the common objective, it is sufficient for process P1 and process P2 to communicate with each other. There's some data which must be communicated between P1 and P2, possibly both ways. Further, I know that it's necessary for process P3 and P4 to communicate with each other. And it might be the case that I also know that towards the end of the program, process P2 and P3 have to communicate with each other. So I know that there are these 3 pairs of communicating processes that have to be achieved through the MPI program. Now, one way that I could handle this is by setting things up so that all the processes are allowed to communicate with each other. An alternative is that I could use this idea of the MPI communicator and note that for the early parts of the program, I have to have one communicator, which I'll call C1, which is defined as the communication between process P1 and process P2. I could define another communicator which defines communication between process 3 and process P4, and possibly a third communicator which indicates communication between process 2 and process 3, thereby avoiding the necessity for declaring all the processes as being part of one communicator, which could potentially have to communicate with each other. But the communicator itself is just the construct within MPI through which the system keeps track of what processes may have to communicate with each other. Now, the way that things are set up is that when you write an MPI program, by default, initially all the processes will be assumed to be part of a single communicator, and we can refer to that single communicator as MPI communicator world. The word world here suggesting that it includes everything, all the processes which will come into existence when this program runs. So in effect, the default will be that the program, an MPI program, would run as with a single communicator. In other words, with the possibility that any 2 processes on the system can communicate with each other, since all the processes form part of a single communicator. This would have been the case in our example if I had not tried to declare communicators, but I had just used the default, in which case when I run the program as 4 processes, they would all be part of MPI com world, the initial default communicator, and therefore any 2 processes in this set of 4 could communicate with each other. Okay, now within a communicator, each process has what is called a unique rank, and I had used this term when we looked at the list of functions in the previous lecture. Essentially, what the idea of the rank is going to do is to serve the purpose of a process identifier. Recall that in doing sends or receives, there was a need to specify the intended recipient by its identity, and I had pointed out that using a Linux or Unix process ID, which is unique on one processor but not possibly unique across processors, since Unix or Linux may keep track of on a given processor may keep track of the different processes that were created for execution on that processor, starting with PIDs going from 0 upwards, and similarly on other processors the same PIDs might be used for the local processes. So the notion of rank abstracts process identification to a level beyond the individual processor. And the way to look at this is, within a given communicator, the different processes which are communicating with each other through that communicator are assigned ranks numbered from 0 through n minus 1. So if there is a communicator with 4 processes, then it would have one process whose rank was 0, another with a rank of 1, and so on, assuming that there are n processes constituent as parts of the communicator. Right? And as I had mentioned, other communicators could be established for other groups of processes along the lines of the upper example which I had used. So the two important concepts we see here are, one is the concept of the MPI communicator with the default of MPI COM world, and secondly the notion that every process which comes into existence when an MPI program is executed will have a unique rank. Now I should point out right now that MPI COM world follows the syntax, the notation that we had seen for the various MPI functions and for the various MPI constants. It starts with the prefix MPI underscore, and from this notation you would understand that basically MPI COM world is one of the MPI constants, suggesting that it might be a constant, let's say with the value of 0, suggesting that the different communicators associated with an MPI program each has a unique constant associated with it, and the default communicator has the constant, whatever the constant MPI COM world relates to or corresponds to. So MPI COM world is one of the MPI constants, which in fact was on the list that we had seen. Now let's just look at a very simple example of an MPI program, just to make sure that we understand how simple it is to write an MPI program. So basically I'm going to be using that SPMD. I'm going to write an example where there's a single program which is going to be run on all the processors, one process per processor possibly, of the parallel machine. So I'm writing the single program in C, so I'm showing you this main of the single C program. You'll recall that any MPI program must start by doing the initialization by calling MPI init. So that's the first thing that I include in my MPI program. And any MPI program must start by end by finalizing, so I put that as the last thing, the last component of main. In between, there could be various kinds of activities that different processes do based on their activity as required by the common objective. The same program is going to run on each of the processors which I specified through MPI run, and therefore very clearly in the code that follows I have to set up things so that the executable as when running on one processor, possibly running as process with rank 13, will do different things from the same executable running on another processor, possibly running as process number 27, right? Process number 27 in terms of its rank. Therefore, what follows must first of all make certain determinations about this particular execution of the MPI program. For example, how many processes are there in this particular MPI program? And there is an MPI function through which the program can determine how many processes this program is running as. Further, there is a function which can be used by any particular process to determine what its own rank is. So we had seen MPI COM rank, a function through which an MPI process can determine what its own rank is. So in this particular call to MPI COM rank, there's a need there are two parameters. One is the particular communicator that one wishes to know what the rank is, and then one passes a parameter into which the return value, in other words, the rank of the process which is running, which is executing this particular function, will be returned in the variable MPI rank. So MPI rank would have been declared as a variable, my rank would have been declared as a variable, an integer variable in this program. So after calling MPI COM rank, the value of that variable will be the rank within the communicator MPI COM world of the process which is running this particular instance of the program. And if I'm running this program on each of 100 processes, each of 100 processors in a parallel computer, then each of the processes running on those 100 processors would receive a different value as its my rank. So you can also see that it's possible for one process to be part of many MPI communicators, and it could determine its rank in each of those communicators by putting the correct number of the communicator into the first slot of the call to MPI COM rank. Subsequently, depending on what this particular process finds its own rank to be, in this particular example over here, I'm sort of assuming that if there are 100 processes, then one of them is going to be doing important work which I designate as the work done by the master process, and the others, the remaining 99, are going to be doing very similar work, which I'll designate as the work done by the slave process. And it looks like I'm setting up this MPI program so that after each of the 100 processes has determined what its own rank is, each of them then proceeds to determine if its rank, to check if its rank is equal to 0, and if its rank is equal to 0, it will run the function called master. Now only one of the processes will therefore run the function called master, but if it finds that its rank is not 0, then it runs the function, it executes the function called slave. And therefore in writing this MPI program, I would write a function called master which contained the functionality to be done by the master process, and I would write a function called slave which contains the C functionality describing what is to be done by each of the remaining 99 processes in order to achieve their common objective. So this is the general structure of this SPMD, a single program which will be run on each of the 100, in this example, processors of the parallel machine to achieve their common objective. So this was just to illustrate the notion of rank and communicator, and how the rank of a process can be determined by the process. Okay, now just to complicate the example a bit, very clearly the reason that we want the processes to know their ranks is partly so that they can each end up doing the right work. For example, the master process does the master work and all the slave processes do the slave work. But at some point in doing this work, there may be the need for one process to communicate with another process. And that's where the calls to MPI send and MPI receive will enter the picture. So in this particular example, we once again have, I'm not showing you the call to MPI init and MPI finalize in this example. We're assuming that this is just an extract from a larger program. But in this example, what we're doing is trying to see how two processes could send, one process could send data to another process. So once again, I'm assuming that each process knows its own rank, and each process can find out its rank by calling MPI_com_rank. Subsequently, the way that I've set things up is I know that the process whose rank is 0 is supposed to send data to the process whose rank is 1. Therefore, in the program as I write it, there's a part of the code which checks if the rank, if the process finds out that its rank is 0, then it is the process which must do the send. On the other hand, if the process finds out that its rank is 1, it is the process that must do a receive in connection with this communication. And the parameters of send and receive we will see about shortly. But you'll notice that in common, if you look at the way things are set up, the process which is going to do the send has a local variable called x, and it is the value of that local variable which is apparently going to get sent. The process which is going to do the receive also has its own local variable called x, which is the variable into which it is going to receive the value. So subsequently, if either of these processes refers to the variable x, they will actually be referring to a variable that had the same value, at least soon after the send and the receive were done. But this is how a send and a receive pair could be set up for process 0 to send data to process 1. And in general, prior to this, we were thinking of process 0 as operating system process 0 and operating system process 1. Now we just think of them as a process who happens to have a rank of 0 when the MPI program was run, and the process which happens to have a rank of 1. Okay, now one of the parameters in the call to send and the call to receive, you would have noticed, was a parameter with the name MSG tag, which is actually referring to something called a message tag. This is another important concept in MPI communication, the idea of the message tag. And basically the reason that a message tag is necessary is because it is quite possible, if you're writing a non-trivial program, the processes which are communicating with each other in terms of needing to cooperate may in fact need to send more than one message to each other. So it may be necessary for process P1, process with a rank of 1, to send one message to process P2 early in the program and send another message to process P2 a little later in the program. So the message tag is one of the parameters in the calls to send and receives, and it is a facility through which it is possible to differentiate between different messages that are being sent between, let's say, the same pair of processes. Right? So the message tag value is carried along with the message in both, and is used in both the send and the receive calls, and provides this capability of distinguishing between two messages that were sent from the same sender to the same recipient. And that is sort of illustrated in this example. So once again, I'm showing you an example, an extract from a larger MPI program. Here the objective is that after the processes have determined what their ranks are, process with rank 0 is sending data to the process with rank 1. So, the process with rank 0 does certain things, the process with rank 1 does other things. In this particular example, the process with rank 0 is doing two sends, first this send and that send, to the process with rank 1. And in order to distinguish between these two sends, it could use a different value for the message tag variable, and once again the message tag is a variable local to the process with rank 1, which could be set up with an integer variable called message tag. So, it is possible that message tag, the first message is sent with a message tag of 1 and the second message is sent with a message tag of 2. Similarly, the first receive could be set up to receive with a message tag of 1 and the second receive could be set up to receive with a message tag of 2. And the consequence of doing this is going to be that whatever was sent by the process with rank 0 in the first message will be received by the process with rank 1 in the first receive, and whatever was sent by the process with rank 0 in the second send will be received by the process with rank 1 by the second receive, and that will avoid the possible confusion about which data is going to be received by which data of sent is going to be received by which of the receives. And you should notice that there is a possibility in a very complicated parallel machine that the two send messages may actually not be received in the same order. So, it's all the more important to have these message tags to distinguish clearly between the data sent by one send and the data sent by another send. Okay, now so the idea of the message tag we understand. We should note that it is conceivable that in a particular program you may have set up the program so that it is not critical that the messages be received in a particular order, and that you do not really care whether the first receive receives the data sent in the first send or the second receive receives the data sent by the second send. So, if the application is such that you do not really care, unfortunately there is no option of mentioning message tag 1 or message tag 2 in both of these locations, and therefore MPI actually gives us an option for message tag, which is what is called a wildcard. It is basically a wildcard indicating that it is not a specific value of message tag, but some general kind of a notation for a value, and this is to be used in the special case where we do not really want to match a particular send and a particular receive, but do not mind which data is received by any one of the receives in process P1 in our example. So, in this case what one would include as the message tag is the MPI constant MPI any tag. So, MPI any tag is what is referred to as a wildcard, to be used in cases where one does not really care what the value of the message tag is. In other words, for the many communications between process P1 and process P2, we do not mind which order they are received by process P2, and therefore in all of the receive MPI calls within process P2 we could use the MPI any tag as the message tag. Right. So, the consequence is that there need not be matching sends and receives. Now, the default as we understand it is that one may use message tags, and that the sender will specify not in the MPI underscore send function call, the sender in our example process P0 must mention what the destination is, in other words that it wants to send it to the process with rank 1, and it could also specify the tag. And at the point of receipt we note that once again the receive function indicates the recipient, not only where the message came from, but also the tag with which it was sent, and that as part of the function receive, an attempt is made to check whether the value of these two fields match with each other. Now, in the case of the tag, we saw that there was a possibility of indicating that we did not care which tag the message came with. The same is also true in the case of the source of the message. So, in the receive system call, it is possible to say, rather than saying that this message receive is supposed to receive a piece of data that was sent by process with rank 0, one could say that this receive can receive data sent from any source using the MPI constant MPI any source. So, it is possible to overcome the default of matching sends and receives using these two wildcard values for the sender and tag message tag options of the send and receive functions. Now, further there are a few flavors to sends and receives, two flavors to sends and receives in MPI, which are what are called synchronous and asynchronous. We have seen these two words earlier when we talked about asynchronous I/O, input and output, and there is a similar flavor to what is happening in the case of MPI. Now, the idea of the synchronous message passing is that after the send and receive routines return when the message transfer has been completed. So, the idea is that I could have a process with rank 0 and a process with rank 1, and the process with rank 0 does a send, and the process with rank an MPI underscore send, the process with rank 1 does a receive. These are both function calls in those processes. If the functions that I have used are what are known as synchronous MPI sends and the synchronous MPI receive, then the property is that the actual return from the function MPI send will happen only when the data transfer has successfully happened. Therefore, the return from receive similarly will happen. In other words, you will proceed, the MPI program will proceed to the next statement in the C program only when the actual message transfer has happened. So, in some sense, one could say that in the case of synchronous send, the process which is doing the send will actually wait until the complete message has been accepted at the receiving end. It does not proceed to the next statement in the program just because the local activity relating to MPI send has been completed. Similarly, with the MPI synchronous receive, it continues execution after the receive only after the data has actually arrived. In some sense, therefore, one could say that the synchronous message passing primitives available in MPI do two activities. They cause data to be transferred from the sender to the receiver, but in addition, they synchronize the processes, because until the message transmission has been completed, both the process P0 and process P1 will be within the MPI function send or receive and not able to proceed to the next point in their program. Therefore, the synchronous sending and receiving provide us not only with the capability of transferring data from one process to another, but also with the capability of synchronizing processes. The asynchronous version, on the other hand, does not provide this facility and may be useful in certain kinds of settings. The bottom line is that the MPI send and the MPI receive do not wait for the action to be completed at the other end before they return and allow the individual local process to continue to the next statement in the program. Right? And this has certain consequences as far as the implementation of MPI send or MPI receive is concerned, because it will require that some local storage be used to remember the message. And the way to think of this is, if there is a function called MPI send, and as soon as the MPI send has transferred the data which is supposed to be sent to a local variable of the MPI library, it can go on to the next statement. Very clearly, there must be this local storage in order to allow the MPI send to quickly go on to the next statement in the program, which is why I reminded you that we have seen asynchronous I/O, where it was possible immediately after a file I/O operation for the process which did the file I/O operation to go on to the next statement in its program, regardless of whether the I/O operation had completed or not. The situation is very similar here. The idea is to allow the programmer to write the MPI program to do other activities after the MPI send has finished some of its activity, in the interest of reducing the amount of time that the process is blocked waiting for the transfer of data to actually complete. So, it will require a little bit more careful programming by the programmer to make sure that the receipt of the data by the receiver is not assumed in the statements that immediately follow the send. Now, we can now look at the parameters of the typical MPI send function. Now, the typical MPI send function has 6 parameters. The first parameter is the address of the buffer which contains the data that is to be sent. In the examples that we had, for example, there was the address of the variable x which contained the value that process 0 wanted to send to process 1. The second parameter is the number of items that are to be sent. Now, until now we were assuming that a single integer value had to be sent. But what if this buffer is an array which contains a large number of integer values? It should still be possible for the entire array of values to be sent. That's why there's this notion of being able to specify how many values from the buffer are supposed to be sent as part of the message. So, if for example we want the first 3 values in the buffer to be sent, then we could indicate that the number of values from the buffer that are to be sent is equal to 3. Now, how big is each of the values that is to be sent? That is specified by the third parameter, which is the data type. The data type specifies the type of each of the elements which is supposed to be included in the message that is sent. So, if for example this is a buffer of integers, then the fact that it is integer is what would be conveyed in the data type. And you will remember that we had MPI declared constants such as MPI int, and this is kind of a situation where one would use the MPI constant MPI int, for example, to indicate that each of the values, each of the 3 values in this example, which is supposed to be sent as part of the message, is of type integer. Now, as always, we know that the destination, intended recipient of the message, must be mentioned in the send call by its rank. Finally, we know that the tag may be used. By default, one could use the MPI any tag if one is not too concerned. And finally, the communicator within which this particular communication is happening is also a parameter. So here, for example, if we are just using MPI com world, the default communicator, then the declared constant MPI com world would be the value of this parameter. At the receiving end, there is a matching set of parameters, which I therefore won't go into in detail. Rather, let me spend a little bit of time talking about 2 other variants on the kinds of sending that can be done in MPI, which are known as the blocking and the non-blocking versions of send. Now, the property of the blocking version of send is that the send call returns immediately after the local variables the local actions associated with the send have been completed, regardless of whether the message transfer has happened or not, as opposed to the non-blocking, where it returns immediately even though after the local actions relating to the send operation have been completed. And again, this will require using the blocking. In the case of the blocking, notice that it talks about returning after the local operations have been complete, whereas in the non-blocking it returns immediately even if the local operations have not been completed. What do I mean by local operations? Basically, one must understand that ultimately the transfer of data from process P1, process with rank 0, to process with rank 1 is going to happen using some underlying operating system functionality, and there will be a need to therefore pass the information from the MPI program to the operating system, possibly by copying it into an MPI buffer, as I had mentioned. And there will be various other local operations between MPI, your program and the MPI library, and also between the MPI library and the underlying networking software on the computer system. So these are what we are referring to as local actions. So in the case of a blocking MPI send, it's only after the local operations are completed that the return will happen from the send, whereas in the case of the non-blocking, even if the local operations have been completed, the return from the non-blocking send could happen. Right? And this once again will assume that there is adequate storage, for example, for the buffering of the information contained in the message. And this may be something that the programmer has to take care of, the allocation of adequate storage for this purpose. Okay. So it is, as I pointed out in the second bullet, a little bit of a concern to the programmer, because the amount of local buffer space which may be available for this local activity may be implementation dependent, and this may cut into the portability of the program that we are talking about, and therefore one must use the non-blocking calls only after carefully understanding the implications in terms of what other kinds of facilities may have to be included in the MPI program, as for example ensuring that adequate local buffer space is occupied. Whereas the non-blocking case will be much easier for us to set up, ensuring that any problems with the amount of local buffer space are not present. Right. So I had indicated that each of the facilities send and receive is actually a collection of functions, because we now understand that there's going to be a separate function for sending a blocking send, a separate function for non-blocking send, and therefore one will come across a family of names. For example, the non-blocking send is known as MPI_ISend, and the parameters are similar. There's one additional parameter because there's a need for this synchronization to understand at what point in time the operation has actually finished its local activity. Therefore, I included this slide just to let you know that in addition to MPI send, one may find other variants in which these concepts of non-blocking or blocking may also be present as different functions. Right? And at the other end, there will be the non-blocking receive, which is referred to as MPI_IReceive. Okay, now in the case of this non-blocking send and receive, there is a need for the sender to actually have some way of finding out as and when the send actually completes, and hence there are additional functions known as MPI wait and MPI test, along the lines of what had to be done in the case of asynchronous I/O, for the sending program, the sending process, to check when the send has completed and hence continue to the next part of its functionality. Now the next important part of MPI communication, now that we have a rough understanding of the nature of the send and receive basic functions, is another kind of communication which is known as group communication. As the name suggests, the idea here is, rather than talking about communication between one process and one other process, we're talking about ways to do communication between groups of processes. And that's as described by this bullet, because until now the kind of send and receive that we were talking about were functions that could be used for what is called point-to-point messages. A communication between process P0 and process P1 could be done with the send and the matching receive. So that's what we refer to as point-to-point message. What we're now going to talk about are communication mechanisms for communication between groups of processes. So possibly one process sending a message to 10 other processes, or 10 processes communicating data to a single process. So these are what are known as groups, a group communication. Now the group communication, as you would understand, is actually not essential for programming, because if you have a mechanism through which you can communicate between one process and one other process, then you could use the same mechanism to communicate between one process and 10 processes. You just have to include that mechanism 10 times. So the reason that MPI includes group communication is to make things easier for the programmer. The programmer doesn't have to include the 10 sends when one process wants to send data to 10 other processes, but rather can just include one of the group communication calls. So it's not absolutely essential, but it makes programming a little bit more convenient. And it may be possible for the MPI library to do that group communication in a more efficient fashion than the programmer may think of, while if he was to set it up, he or she was to set it up using point-to-point communication. Now, the examples of group communication which I'm going to talk about are the kinds of group communication which are generically known as broadcast, gather, scatter, and reduce. I won't talk about barrier. I'll talk about barrier as an example in the next lecture. So what are broadcast, gather, scatter, and reduce? Now, they are all functions which are available in MPI. For example, the broadcast function is available in MPI by the MPI function MPI underscore bcast. Similarly, there's MPI underscore reduce, MPI underscore scatter, MPI underscore gather, and so on for the various other kinds of group communication. First of all, let's try to understand what the broadcast functionality is. I'm going to describe this diagrammatically. So the situation is, let's suppose that I have a parallel program which is running as n processes, and the processes have ranks 0 through n minus 1. Now each of these processes is going to run, let's suppose, on a different processor. It's going to run the same program, and let's suppose that I have a requirement that I want a particular piece of data to be communicated from process 0 to all of the other n minus 1 processes. This is the kind of situation where which I can achieve using a call to MPI broadcast. So at the appropriate point in the program, I would include a call to MPI broadcast so that it is executed by all of the processes. And what this is going to allow me to do is, it's going to allow me to communicate a single piece of data which is part of the address space of process P0 to all of the other processes with a single communication. So with this single call, I have been able to broadcast a value to all the other processes. Remember, the alternative would have been that the process 0 would have had to do a send to process P1 followed by a send to process P2 and so on. It would have had to do 9 MPI sends, and each of the processes in turn would have had to do an MPI receive. But the net effect would have been that the programmer would have had to write a more complicated program. In the current version with broadcast, the programmer just writes this very simple program in which each of the communicating processes just does an MPI broadcast. Now obviously there's going to be some interesting parameters in MPI broadcast, because they were all executing the same program, which means that the fact that process 0 was the process which was doing the broadcast and that the other processes were the processes which were receiving the broadcast must somehow be indicated within the function call. If we look at the parameters to MPI broadcast, that's what we'll find. We'll find out that in addition to the buffer count and data type which was present in MPI send or MPI receive, and in addition to the communicator information which was also present in MPI send or MPI receive, there's one additional parameter which is what is called root. And the root is basically the specification of which is the process which contains the data that is going to be broadcast to the other processes. So in our example, the example which I'm referring to is this one. It is process 0 which is the root of the broadcast. In some sense it is the root from which this tree of information is going out to the other processes, and therefore the value of root we would find would be equal to 0 in all of these calls to MPI broadcast. So MPI broadcast is a function which is provided in the MPI library for this kind of group communication, and as you'd imagine, this kind of group communication may be fairly widespread. may be necessary for lots of different kinds of parallel programs, which is why it is provided as a basic function of MPI, of the MPI library. Now, the next function which I talked about was a function called scatter. We are talking about the different kinds of group communication functions provided by MPI. And once again, we'll look at it diagrammatically. So we have a situation where there is a parallel program running as n processes. And once again, a single call to MPI scatter is going to satisfy our requirement. Now, what is the requirement? The requirement is that I have a collection of data which happens to be present on, let's say, process P0 in a buffer. And what I want to do is I want to distribute the data which is present in the buffer across all the n processes of the parallel program. To be more precise, I want the first element in the buffer to go to process P0, I want the second element in the buffer to go to process P1, and so on. Now, this primitive operation is what is known as a scatter, and the name makes sense once you understand what it does. Essentially, I had this collection of data and I want to scatter it across the different processes of my parallel program. In this particular example, one element going to each of the processes. So very clearly, once again, if we looked at the parameters of MPI scatter, we should find out that it should mention both the buffer as well as the location into which the data is to be scattered for that individual process. In addition, the identity of the root of the scatter must be indicated. In other words, the fact that it is process 0 which actually contains the buffer which is to be scattered across all the n processes. It is important to note that unlike the case of broadcast, it is the scattering of the data includes process P0 or the root of the scatter within it. So we expect that the parameters are going to be very similar to what we had in the case of broadcast. In other words, this set of parameters. The only additional parameter that we will have will be the buffer which is going to be into which the scatter is going to be done. Notice that we had both a buffer from which the scattered data came and a buffer into which the scattered data goes. So one additional parameter in the case of scatter if compared to the broadcast group communication. We'll now move to gather, and as the name suggests, this is going to do the opposite of what scatter did. In other words, it's going to gather data from n processes into one process. So once again, in a parallel program running as n processes, we suspect that there is data which has been scattered or which is available one data item on each of the n processors, but that we want to gather it into a buffer within one of the processes. Let's suppose that it is process 0 which contains that buffer. So the effect of the MPI gather call is going to be that the data is going to come from each of the variables data in each of the individual processes and get put into the appropriate slot in the gathering buffer. In other words, the data from process 0 goes into the 0th element of the buffer, the data from process P1 goes into the first element of the buffer, and so on. So this can be, as you can see, by scattering data and subsequently by scattering data, it might be possible to, for example, distribute work to be done by the individual processes of the parallel program. For example, if I wanted to do some computation on each of the elements of this array, then I could write a parallel program which scatters the data across the processes of the parallel program. The processes could then independently operate on their portion of the data, and after the computation had been completed, they could conceivably send their newly computed value back to process 0 using a gather. So one can see that in certain applications these kinds of group communication could be very useful. There was one other group communication primitive that I had included in my list, and that was an operation called reduce. Now, as the name again suggests, here what's going to happen is some large collection of data is going to get reduced into possibly a single value. And in our scenario where there are n processes, we would understand that the objective of reduce must be to take data which is present one value on each of the processes and somehow combine it into a single value which will be available on one of the processes. So the question is, what kind of reduction operations might be possible? We have come across the notion of a reduction operation earlier. I talked about the notion of a vector sum reduction. You'll recall when we were talking about the different when we were looking at cache optimizations of loops of programs, one of the operations that I talked about was a vector sum reduction, where essentially we were computing the sum of the elements in a vector. And that is an example of a reduction operation of the kind that we are talking about over here. So the reduction that we are talking about might involve gathering the values from all of the processes in the variable which they individually call data into one of the processes, and at that process reducing it, but maybe by adding all the values together to produce a single value which might be the result of the MPI reduce call. So in MPI reduce, obviously the parameters would be like the parameters in scatter and gather. There must be mention of the individual data items, the variable which is going to be reduced, and also of the buffer into which the accumulation is going to be done, or the reduction is going to be stored. What are the different kinds of reduction operations that are supported by MPI? MPI, okay, here I have actually shown you the parameters of MPI reduce. As we always suspect, there is going to be the need to specify the communicator in which this communication is going to happen. In this particular situation, there is going to be the need to specify both the buffer into from which the data is going to come. So this is what had been referred to as data in my example, and the buffer into which the reduction is going to happen, which was referred to as buff in the example. Some indication of how much data is going to have to be accumulated and of what type from each of the buffers, and which is the root of the reduce operation. In our example, the root was 0. And finally, what operation is going to be used for the reduction. So one has options about a few different operations which could be used in the reduction. The two which I'll mention are, first of all, the possibility of actually doing the sum of the different values of data using MPI sum as the reduction operation. Another possibility which is supported is to actually compute the maximum of all those values, and this again may be useful in certain kinds of parallel activities. So in short, there is a family of these group communication primitives through which it is possible to improve the performance of an MPI program by utilizing the improved version of communication as an alternative to individual processes communicating values by separate sends and receives. Okay, now as a closing example, I'll go through one more example after this, but just to sort of put these things together, here we have, let's say, a situation, a brief MPI program which you'll notice is using 3 of the MPI functions. It's using MPI rank, it's using MPI size, which I haven't talked about. Let me say a word about that. And it's using MPI gather. Gather is the group communication function which will gather values from each of the n processes into a buffer, an array in the root process. Now the objective of this particular program, as the comment suggests, is that there is a collection of 10 pieces of data, and that we want to gather it into one of the elements of one of the processes of the MPI program. So this is declared in all of the processes which are running. So in this program, each of the processes determines its rank, stores it in its local variable myRank, and depending on whether the process is the root of the group communication or not, if the process is the root of the group communication, then it finds out the size of the communicator. Now MPI comm size is one of the functions that we had seen in our list of functions, but I had not talked about. What MPI comm size returns is the size of the communicator in question, and by size we mean the number of processes involved in that communicator, or the number of processes in that communicator. And therefore the ranks of the processes within the communicator would go from 0 up to group size -1. And you'll notice that what the process which is the root of the communication is doing is it is allocating a buffer of adequate size to hold the data which is going to come from each of the processes which is going to be involved in the gather. So it declares a buffer which is going to be the buffer which is used in the call to gather. Now the data which is going to be gathered is going to come from the individual processes. So each of them has data inside its data object data, which is going to be another of the parameters. So data is going to be another of the parameters in the call to gather, not listed here. Each of them is going to provide 10 pieces of data from its 10 pieces of data. That's not the way things are set up. The way things are set up is to do this using gather. You'll remember that in gather we actually had a piece of data coming from each into a global buffer. So in this example, the global buffer is of adequate size because it has been declared to be of that size, and the individual values are coming from the individual communicators from their buffers called data, which must be specified as the other parameter in the call. Now from each of so buffer was missing in this particular list. From each of the buffers, you'll notice that 10 values had to be communicated, and that each of those values was an integer, which is why we talked about communicating 10 values each of type integer, from each of the processes to the root process into the buffer. That is why buffer was of size 10 multiplied by group size multiplied by size of int. So if there were 10 communicating processes, then buffer would have been of size 100 multiplied by the size of int, possibly 400 bytes. So this was a slightly more complicated example, but what we will do in the next lecture is to actually look at a specific example of a computation as a MPI program in completeness, and then we will proceed to look at some examples of writing parallel programs, not specifically in MPI, but from the perspective of understanding how the activity of writing a parallel program from specification of the problem until a clear identification of how the different processes might be viewed could be conducted. And we will stop here and proceed with a more complete example of an MPI program in the next lecture. Thank you.